Hi, everybody. I'm going to tell you today a little bit about some of the things that we have planned in the cognitive science thrust of this expedition. And of course, Josh would have done a much better job than what I'm about to do here. But I see that Noah is in the audience and so is Zena. And I'm hoping that as CogSci experts, they'll be able to field some of the trickier questions that I may not be able to answer. Okay, so first of all, our highest level objective in this thrust is to take some of these tools of neurosymbolic learning that we are going to develop in this project and apply them to understanding the cognitive process itself, understanding the mind. And so when we think about how the mind picks up new concepts, new languages, new social rules, how the physical world works, rules of mathematics, programming, all of these skills, there is a computational process going on there. And what we are trying to do over here is to capture that computational process in code. Now, when one thinks about somebody who learns, the immediate thought is that of a child. And there is a longstanding hypothesis in cognitive science that the child is a scientist. When you are thinking about childhood learning, it's very much like the scientific process because children go and define intuitive concepts about the world and then go and test these concepts. And then they sometimes figure out that they need to go in and try the same thing that they did, maybe with a little variation. And you can think of that as the child seeking out data that distinguish hypotheses and isolating variables and testing causal hypothesis and so on. So just to give an example from my own life, I have this adorable 15-month-old, Atish. Yesterday, he got his finger pinched in a cupboard. And first he yelled, and then after he was calmed down, he just went back to doing the same thing, but with a little bit more force. And of course, he yelled again, and you can imagine how it was for the parents. But the point is that this is, an n=1 data point for this hypothesis of the child as a scientist. Now, the way this relates to the current project is that some folks, such as Noah and Josh and Zena and other folks in their team, they have been for some time advocating the idea of the child as not only a scientist, but a computer scientist. And so what this means is that these concepts that children hold, these concepts are very naturally represented as programs. So let's think about something as basic as counting. You can think of the concept of counting as a program, as a computation in a number of different ways. So one way to think of it is that given a number n and a set x, decide if x has n elements. But there could be other programmatic ways of representing this too. Maybe you're given a set x and you have objects of different types, and you're thinking about the concept of counting as this function which returns the number of objects of type t in the set x. Or alternatively, you could also think of a function where you're given a number n and you're just returning a set of n elements. And these three are by no means the only ones. You could imagine adding more functions of this sort. But the point is that these concepts are programs, and so the process of acquiring these concepts through a series of experiences, that you can imagine naturally as a form of program synthesis. So you could imagine the child that's just starting out in the world as having a prior over these programs, and these programs represent causal models of the world. They capture, what happens when you stick your finger into a cupboard and then you shut the cupboard door. You have this causality embedded there. But they're also compositional because presumably when you have one piece of knowledge, you have another piece of knowledge, you are able to put them together into new concepts. This is something that we do all the time. And they're probably also probabilistic in the sense that they're able to represent uncertainty about the world. So these are the kinds of programs that we have. And when you're starting out as a child, you have this prior over programs. Now, as new experiences take place, you are updating this prior. And then you're also constructing, new programs by using something like Bayes' rule, but also through composition of these simpler programs. So let's try to make this somewhat concrete. Let's think about, again, this problem of counting, and let's think about the process of learning to count. Now, here is what is known from work by Josh and Noah with Steve Piantadosi from about 8 years back. So what is known is that when children first learn to count, they first learn a list of counting words without knowing any sort of meaning. They just know that you have words such as 1, 2, 3, 4, and so on, up to some length. And then they pick up the ability to count subsets up to size 1, and then 2, and then 3, and then very rarely 4. 5 plus is never, so far as I know, it's never been seen. This goes on for a little while, but then around age 3.5, they suddenly learn the principle of counting. So the principle of counting is something like this. As you are going right on that list of words that you have, so let's say that you have 1, from 1 you go to 2, then 2 you go to 3, from 3 you go to 4. As you go move one step right, then there is an extra element in the set being counted, right? This is something that's completely obvious to us as adults, but this is not something that is obvious to toddlers. And this is something that they only figure out around age 3.5. And so this learning process, for which there is evidence that goes back to actually before this paper, but this paper was able to give this computational model which explained how this process works. And so here's what that explanation looks like. So we are going to, again, think of these concepts of counting as programs. So when you are one knower, that is, you know only to count up to subsets of size 1, you can be imagined to have a program like this in your mind. So this is written in the lambda calculus. So what this is saying is that if you're given a set, if the set is singleton, you say there's 1. Otherwise, you just don't know. It's undefined. Two knower is going to say, and by the way, the task over here is you are given a set, you are deciding, right? How many objects are there? Okay, so now for two knower, it's that you know 1 and 2, but you don't know anything beyond that. For 3 knower, it's that you know up to 1 to 3 and you don't know anything beyond that. But then what explains this ability to this abstract ability of that says that if you move right by 1 step in the word list, then there is an extra element in the set being counted. And so a natural way to think about this is recursion. And this was their hypothesis, and their model was able to actually explain the data that was there using this kind of a model. So when the child reaches this age 3.5 milestone, they are figuring out recursion. So now, okay, that's fine. So these are the kinds of programs that are there, but how are we modeling actually the learning process? So they viewed it in terms of Bayesian program learning. And so the context here is that you have a set of types of objects, such as cats and dogs. And then you are experiencing a set of contexts. And in each context, you are seeing a bunch of typed objects. So for example, in the first context over here under this, in this set C, you're seeing 2 dogs, a cat, and a horse. And then when you're seeing these contexts, you're also getting words associated with it. So for example, when a child sees a scene with 2 cats, maybe they hear the words 2 cats, right? And so there is an association that is formed. And so now what we want to do is to learn this distribution over programs, P of L given W, T, C, that is The set of counting words is given, the list of counting words is given, the set of categories is given, the set of context is given. And now you are trying to infer this distribution, P of L given WTC. And you can imagine using Bayes' rule to basically invert this distribution. And then you get something like this equation over here. Now, one question is that, what is this prior that you're using, and how do you get that model of W given TCL? There were assumptions made about this in their paper. For example, the prior was supposed to prefer simpler programs over complex ones. But the point is that they were able to instantiate these component distributions in a way as to explain the observed transitions in the counting knowledge. And the specific algorithm that they used was Markov chain Monte Carlo. But as I'm going to say in just a little bit, one of our objectives in this project will be to bring in more sophisticated algorithms that are able to scale better to this sort of domain. Okay, so I'm just going to talk about one more setting over here where this sort of concept learning makes a lot of sense. If you think of how people learn visual concepts from just a few examples, this can arise in the setting of classification. So that is this figure 1 over here. You are given all of these different kinds of vehicles, and you are trying to classify them as something similar to what you have at the top in the red box. But you could also have other things such as generating new examples, parsing a complex object into parts, generating new concepts, and so on and so forth. So a paper from 2015 by Josh and Brendan Lake and others, this used a program learning model, a Bayesian program learning model, to explain this sort of visual concept learning. And what was interesting is that this model, which was a generative model over programs, and the programs were fairly simple, though compositional, they were able to outperform deep learning, at least as deep learning was at that point, on one-shot classification. So where do we go from here? This is all stuff from a few years back. The challenge that we have right now is that these underlying questions have not gone away at all. In fact, even counting, as I will show in just one slide, still remains an unresolved question. And there are, of course, so many other places where human cognition just performs in a way that is amazing and that cannot really be emulated by any machine that exists today. So we need to keep trying, though. So one way in which we can move forward using the tools that get developed in this project, that's to use richer models and learning algorithms. So specifically, you can imagine more sophisticated probabilistic programs, more sophisticated priors and generative models. One thing that is especially important is combination of symbolic and sub-symbolic modules. So the kind of program that I've showed so far, these are fully symbolic, but you could imagine models where you have symbolic pieces for the higher level reasoning parts, but then you also have modules that are neural networks that capture maybe representations of the world, maybe learned through self-supervised learning or something like that. And then, of course, there is the question of how do you do inference. The way they did things in those earlier papers, that scales up to a point, but presumably with our learning accelerated and solver-aided program synthesis techniques, we'd be able to learn much more complex models and thereby explain much more complex phenomena. And this can also lead to new experiments. For instance, we can try to devise new experiments that classify skills as being hard to learn or easy to learn. We can experiment if we can accelerate children's learning with a suitable curriculum, and you can imagine all of this has immediate applications in the context of education. So I'll just say that I said just a few seconds ago that even counting is not fully explained. Here are just a couple of examples. It seems like children who have mastered counting partially, they do not understand set size. And some of them do, some of them don't. And presumably more complicated models would be helpful in explaining this kind of phenomenon. Also, there are results that show that there are differences between industrialized societies, children raised in industrialized societies, and children raised in farming foraging groups. This is presumably dependent on complex environmental phenomena, which were not modeled by the existing models, but these are things that we could imagine modeling using our more powerful set of tools. So there are other contexts where we are looking into these sorts of questions. Specifically, some of us are looking into the so-called abstraction and reasoning corpus, which is a data set that's been, or a problem that has been defined to capture sort of the essence of intelligence. So here you have IQ test type questions. So let's say that you're given a few of these examples of patterns being mapped to other patterns. Now you are asked to fill up that question mark. This is something that humans do all the time from a very small number of examples, but this is very difficult for automated machine learning algorithms. But and presumably solving this kind of task would require us to get into, do sophisticated meta learning or develop other kinds of techniques that that are just not there yet. And that's one thing that we hope to do here. And finally, some folks in Josh's team, and I believe Zena and Ria are leading the development of this environment. They have developed this very interesting environment which models active causal discovery. So you're given a scene, and then you're able to click in various places. You're able to probe this scene, and then that's an action that leads to new things happening. So there is an environment that is getting updated as a result of your actions. And so humans are able to figure out, of course, cause and effect from this kind of exploratory play. But can we explain how all of this stuff happens using a computer program, using machine learning, neurosymbolic machine learning? That's one of our objectives. And as part of this, Zena and Ria and Josh and others they're in the process of releasing this corpus. It's a causal inductive reasoning corpus, which has data about how humans actually explore that environment that we described in the previous slide. And the great thing here is that by looking at how humans actually come up with new exploration strategies, that is something that we can learn from when we are trying to model this sort of exploratory exploration in an unknown environment. And so I'll end with this slide, which captures, in my opinion, the essence of what all is going on here. Deep learning has, of course, been an amazing engineering achievement, but there is also a natural connection between deep learning and computational neuroscience, in the sense that you can think of neural nets as models of the brain. And when you are learning, when you're coming up with new learning algorithms, you are kind of mimicking what the human brain does. And so the analog is that cognitive science operates at a higher level of abstraction in the realm of concepts, higher level concepts and reasoning. And program synthesis can really be the analog of deep learning for this level of abstraction. And just as insights from neuroscience led to engineering achievements in deep learning and vice versa, we can imagine a two-way arrow going between program synthesis and cognitive science. And for this reason, I'm extremely excited about this thrust of our project. Thank you very much.